we have a couple of case studies. For this is a bridge in California, which was designed many years ago, and to address the earthquake problem. This is a very unique bridge because it's heavily curved. Once you have heavily curved bridge, and once you study structure analysis, you will realize that it has all kinds of torsions, and so it's like if you have simply individual piers, and that the earthquake load, no matter which direction you apply, you may have problem of torsion, which at the abutment it will have very large deformation, and at each piers it may have not only a longitudinal transverse, also have torsional load. So that's why the structure analysis become complex. Of course, once you have a finite element analysis type of model, it will be very straightforward. When it was designed, it was not that sophisticated. That's why when they did rehabilitation, they reanalyzed the structure. They found a lot of deficient areas. So for earthquake design, in theory, you need to apply for all kind of X direction, Y direction, and anything in between kind of situations. But that's typically for longitudinal, for straight bridges. For bridges in this nature, probably you need to apply load in different angles, just try to see how the load may affect the structures. And also, when you have different angles, the stiffness may not be the same at different situations. So that's why basically just take that as an example how they will be fixed. So to resist the torsion, very much most effective ways is to restrict at abutments. Once you have both ends restricted, the torsional force in the middle piers will be minimized. And that's why they introduced a bracket. This bracket will restrict longitudinal movement. The longitudinal movement is actually just a tangent to that the curvature, and also that will provide, because you cannot use a cable. Cable can only resist restrictions in one direction, so they use very rigid restrictions. That also restricts you from transverse swinging, because the transverse swinging effect is very significant for that heavily skewed bridge. And these are basically the details, and so they try to these are over piers. Over piers is the same. We try to link a lot of structures into the pier bend to prevent them from free to move. And they have very much similar details as at abutment. Abutment has similar details also as piers. They provide a sufficient strength to tighten that up if it's a fixed. And these are basically the bracket details. And these are the additional connections. They found that there's a insufficient connection at the joints. To increase joints, you could just simply cast a reinforced concrete to cover that everything, so to make that monolithic, so that the weakness of the connection will become non-consequential. And these are just sketches of how they fix these bends. Typically they have strengthened these joints and also these joints, so that when the load apply transversely, of course, it's okay. It was designed for. But the problem is the load, when earthquake comes, it twisted in that direction. That's why once it's twisted, this connection was only designed for in-plane action, so it does not have rigidity to twist. That's why you need to introduce another direction. In these, typically you can have this very so rigid, you can resist twisting. At the piers, you can provide another connection to the pier, so that once you have another direction, the twister will become another issue. Actually, twisting at connection is very essential. We all know there's a bridge failed in Minnesota. The Minnesota bridge, of course, that's cassette plate. Cassette plate is typically designed for in-plane actions, but in that reality, the cassette plate has another links. So it has introduced a perpendicular force, which is in a very weak direction. That causes a lot of stress and deformation, and that is part of the reason it collapsed. There are many, many reasons, but that's just one of the reasons. In this case, if you make a rigid connections, it introduced, it will be able to resist that torsional force. And again, I said, make it monolithic with a bigger concrete encasement that can resist all direction, even rotation, and very much that's a major concern. And these are the details of how they reinforce these connections. So the key element is that they introduce another component to link to the superstructure to resist that out of plane force. And these are connections. Basically, that connection will have enough resistance. But again, that force is not very large. Once you fix your two abutments, because the whole thing is if the abutment side is free, there will be a lot of torsions everywhere. Once the two ends are relatively restricted for transverse movement, the torsional force becomes much smaller. And these are just the additional connections they produce at the kink, because it's a torsion. The girder itself is not curved. For older bridges, the fabrication process is really not as sophisticated now. Now we can just build a curved girder. Before, the girder is straight, so they have we call kink an angle at each girder, so the connection that plate is also very essential to restrict the movement. So before they only have a very weak connection, and now you introduce a tension rods at the bottom. Once you introduce tension rod at the bottom, that will prevent the girder superstructure moving that easily. Because once you move, that will introduce a force that will push that back to the original shape. Yeah, these are the very much detail. Again, whenever you introduce something to the existing structure, try to use a bolt connection. Don't weld anything to the existing structure. And these are another bridge which is very similar. That's a concrete bridge. If you have this kind of situation, you can use cable. Basically, just have cable to connect from that pier all the way to that, and that. Usually, if you have a roundup, you can actually tie that easily. You can stress that. If you simply connect these 2 points, you can prevent that from like a longitudinal movement. It will not be able to restrict transverse movement much. And once you do like this, that will restrict both movement. Like if it's a straight, you can like do like that. It's same as like a steel, as I said. If we introduce another direction that's restraint, then you will be able to constrain that very easily. That is much better than simply have like constraint, like a loose constraint. Loose constriction typically used for like a very simple single span structure, so that you don't have to worry about any transverse movement, because that does not restrict transverse movement much. And these are basically just the details of these constraint laws. So these are just two very design examples. And these are for known foundations, but in many cases, when you do a structure analysis, you may find the foundation is insufficient. In this case, actually, these 2 bridges were designed for earthquake, but at that time they did not have computer to analyze, so they use simplified approach to do calculation. Assume it's straight, and now you find that since it's curved, the force may have different effects to the pier. If we have solid pier or concrete pier, they are strong to resist torsion. That's okay, because they have very, very weak. It's just a steel, like a truss type of pier. It does not have capacity to resist torsional element. That's why they did that. And so if the structure was not designed for earthquake, most likely you may find the foundation is insufficient. Foundation is insufficient, relatively simple. It's just to calculate what new pipe group will be required. You just add new piles outside. If you have loom, like a header loom, you may just drive regular steel piles. If not, you may just do as like micro piles. Micro pile does not need a very big equipment, with high overhead clearance. You just do like that. Again, these are very typical scenarios. Other scenarios, as I said, there will be the three things we discussed earlier. One is prevent it from falling down. That one you simply lose cable constraints. Another is if the shear column is too weak, you may just enlarge it, or just if it's a little bit too weak, you just wrap up with FIP materials. And another is like folding, as I said. Another thing we do a lot is making good continuous. I discussed it earlier, and we had like I just emphasize this. That's why I repeat again. Whenever you have chance to make a good continuous, by all means. I think especially if you're in a region that you don't have big temperature change, like here, your minimum temperature maybe only 10 degrees. The maximum temperature maybe 40, 42 degrees. So you only have that small range. So that way, making them continuous does not really introduce a big stress or big requirement for your expansion joints or bearings. That's actually a very good way of doing it. So like for making them continuous, like if it's concrete, you typically just introduce a big diaphragm to connect all the girders, and then you have like you make it monolithic so that you may actually punch a couple holes in your web, but you don't have to. Like if you have sufficient transverse reinforcement going outside girder, this can actually discontinue at each girders. But most people will just drill holes to let this reinforcement continuous. and then you just make sufficient reinforcement that to resist the live load continuous moment in all those negative bending moment. And that also be applied to steel girders. Steel girder, we just show that in the morning. So all you need to do is that it just build build a big concrete diaphragms, build concrete punch some holes and build a new a diaphragm reinforcement. Just the exact same as the one we showed in the previous slide. And these are one of the favorite options. So every time I see a deck replacement, I just always try to see how many expansion joints I can eliminate. That not only increases capacity a lot, most importantly, it will reduce the future maintenance cost. Okay, yeah, this case study is for using FIP material. FIP, as I said, has become more and more popular, but and this was actually provided by Federal Highway Administration. And at that time, FIP material was not very, very popular. So, and Colorado has built and rehabbed a arch bridge using FIP, and they say I should just use that to introduce FIP so that more and more people will be able to use that. Basically, that's the old bridge. It was an arch bridge, and it has a bridge deck on top of that with some column supports. And the concrete was heavily deteriorated. And so at that time, the designer, what designer decided was that bridge totally shut down. For this type of bridge, there's no way to do a staged construction. It's extremely difficult. So bridge was shut down so that they take all the bridge deck and take all these pier columns and pier bands off. So what's left was the arch. And the arch was not, actually did not have sufficient strength. So what they did, they're using FIP material to reinforce these arches to make it sufficient. And one strategy they used was, because they have to shut down the bridge, so they want to minimize the duration of shutting down. So they did prefabrication for everything. So they prefabricated and got ready, and then only when they got ready, they close the bridge and remove the bridge, a deck, and they build a new one. So this is a scope of work, very much just only thing left is the arch. So that's the original design. The original design was not very good, and they have a lot of expansion joints. It's very strange to me to have a lot of expansion joints for the whole arch bridge, because the whole arch is one structure. So really, you only need expansion joints at both ends. And a lot of these problems is caused by expansion joint leakages. So before during the design, before actually the design was complete, they did they took a lot of samples, coring samples to determine what concrete strength was. And they did finite element analysis to see where the arch was deficient, so that they can reinforce it. And also they designed the new superstructures. And these are the constructions. So they use a FIP strip for longitudinal reinforcement, and then use that strip transversely as shear reinforcement. And some area needs a lot of near support, needs large shear, so they actually the wrap all solid. And they try to use the precast. The precast look the same shape as original, and that's the original they took off, and that's the new one. to speed up the construction. And that's the construction, during construction. So they of course, they remove all the deteriorated concrete, and then they patch the concrete remover. They didn't use regular concrete, they use shotcrete. Shotcrete is much faster. And then after that, they just using like FIP. These are like coring samples. So the coring sample gives them test results for concrete design strengths. So the original design was 3.3. Sorry, the original design I think was the same. It was like 2.5 psi, and the testing from core is the same. So the concrete strength did not change. It was the same. And the original rebar was like a very old rebar. That's actually the square rebars. It was like 33 kSi. The new ones they use the new concrete like 4.5 kSi, and the 60 kSi for just regular reinforcement. And shotcrete concrete use that. And actually, you will see like once they remove the concrete, they found like the original rebar did not have much corrosion in arch because there's really no much salt get into this arch, so that the rebar still did not have much rust at all. These are operations like this. First, they just sealed a crack with epoxy, and then they applied a shotcrete to the area where the poor concrete was removed. And after that, for like a small imperfections, they did not use like any concrete or a cementitious compound. They just simply use like a epoxy paste just to fill these small imperfected areas. And then they use FIP material to reinforcement, that's applications. When you do the application, make sure that it's grooved very well to that you don't have any air bubbles inside these materials. And that's a design. So basically, it's not like a random construction. It has drawings shows how much strip FIP material should be applied at which locations. Just like when you add reinforcement into any structures. And then there's the testing. They have a special equipment to do a bonding test. That equipment will apply to this. Then you just pour that. And if you pour out with a chunk of concrete, that means it's successful. If you pour out with only FIP and no concrete with it, which means it's a bonding failure. And if you did not pour out anything, that is just testing failures. You have to redo test. So of course, nobody wants to see the black because then they typically will coat the most of the bridge rehabilitation you will just coat the FIP material with the concrete color so that it will look like a concrete. Yeah, these are materials they use, and that's a material specification they use for the design. And again, all the elements were precast, like a pier, a column, pier bends, and the pier bends installation. And even the deck is precast, so the deck will be cast that. Once the deck is installed, there's two ways. Some people may apply a concrete overlay, another reinforced concrete overlay on top. But in Colorado, they use the same system like in Canada. They use waterproofing membrane. Basically, these joints will be, of course, cast with concrete. So you cast concrete into these joints, and then what they did was they apply like waterproofing membrane. Once you apply waterproofing membrane, then you apply pavement, asphalt pavement on top. And of course, after the completion, usually the politician will show up and have cut some ribbons and take some photos and take credit. Actually, they had a cake made of that image. So that's new. The new one looked exactly the same as old one. Only difference was actually the bridge actually has a lot of FIPs, although you don't see it. And these are the, like a general arrangement where the FIP material and how they should be applied. Okay. Yeah, that's the third case studies. Another thing people are actually always thinking, since deck get corroded and deck needs repairs, and why can't we just make some material that does not require any repairs? Actually, it's possible. Like, for example, FRP can be used for bridge deck, but because it's so expensive and it's not really practical to use. Although in the United States, most of states has one or two such bridges, but they typically use like research grant. They apply for research grant to get the funding for the construction instead of using regular funding for bridges. These are actually, I only designed one, and I don't think I will be designing any other ones in the future. But as I said, the advantage is very obvious. It's very lightweight, and installation will be very rapid, and also it's corrosion resistant and low maintenance. Some people may say maintenance free. But these are very, very important, especially these two. It's very essential characters, but and the only problem is cost too high. And because there's not too many markets for these products, so they don't produce a lot. For example, and the manufacturer I use, actually that manufacturer has shut down because they couldn't sell any such products. Nobody buy it. So that's why they only have like two sides. Because this deck is very, very strong, so you don't need to design. So they say how do you design? Because since they have only two sides of member, they say if you have a support less than 5 feet, you use that 5 inches. If you up to 10 feet, you use 7 and 7.6, which is 195. Actually, it was using metric for the design, so that you only have. Okay. Since you have only 2 choices, then you only have that. And in general, if you design something new, especially for new product, and normally the designer don't have as much experience as the manufacturers, because these manufacturers have fabricated or built quite many such bridges already. And the best source of information you can get is from the manufacturers. Okay, how many other bridges has been designed, and how they designed this project, and you get information from them, and from there you just take a look to see if there's anything you can improve or if there meet your requirement. Otherwise, you may just use what their details are. So how these decks were built? And the deck is made of these a tube, a plate with tube things with voids, similar to a void slab, but it's just very, very light. So it was made of when they fabricated, it was about that wide. And in the factory, they glue them together to form about like 3 meters wide. The reason 3 meters that they can put into truck easily to transport. And then they will make it this wide, and they also have some holes on top. These holes will be designed to match whatever shear starts or whatever if it's concrete, where like shear reinforcements are. So that will be the detail for either steel or concrete structures. And the railing detail, they have a couple of these, but my recommendation is that just try to design the railing which is independent of the deck, so that don't put the railing on this deck, because we don't know what the performance may be. Like if you use these, that's okay, because that has nothing to do with the deck. Or if you use these concrete, like this will be all solid concrete, so that will be something we know. And basically construction. Construction is very rapid, so you basically just deliver these panels to site and load, and you just apply this epoxy material to like the joint, like both like a female male side, and then you just glue them together. And after you glue them together, you put a like FRP tape on top. Like that's once you glue it, actually. And before you put the FFP tape, you actually drill some holes and put some pins into that joint to prevent them from movement. And then you just tape them up longitudinally and transversely to make them into one piece. And then it just like put a well, like a shear starts into these holes. And after that, you just put grouting into these holes. And then that's much. After that, you typically do a pavement on top. And so this pavement typically very thin. And they use like a epoxy modified asphalt, not just regular asphalt, so that it does not need to be very thick. And yeah, these are actually these are one of the bridges I designed. And for rehabilitation project, because original these are original stringers on a truss bridge, and because the original deck has like a slope. Actually, that bridge had 1% slope, but you can only have one panel, so you cannot bend the panel. So what you can do is that you just weld angles, like very light gauge angles, to the edge of the top of flange, to make up the height difference, so that it will be totally flat. So you can put that in. Like from underneath, you will see like these panels very neat, look like plastic. Yeah, that's final product. That's a bridge. This is like a computer model of how they do it. Like you have like FIP deck. You have like epoxy modified concrete pavement, and these are just a concrete. You build additional concrete curb, and the concrete curb. Once you have concrete curb, these will be built on top of concrete curb. So the railing will be typically like standard drawing. You don't have to develop new details. Same as like expansion joint. Basically, you just punch some holes in these stringers, and you build a concrete diaphragm. Once you have concrete diaphragm and you have concrete abutment, so you can build expansion joints from concrete to concrete as like a regular concrete. So these are the curve details, and these are just like expansion joint details. And so that's give us some experience of how to build these. These bridges are very easily to design. You really don't need to do any calculation. They're so strong, so they're really deflection controls. All you need to know is that what's your girder or stringer spacing. So you decide what thickness you need. And since the manufacturer has only 2 thicknesses to choose, you just to choose the one that appropriate. And we only produce some drawings, and there's no, most of the detailed drawings are from manufacturers. They recommend to use that way. So all we develop is what kind of like a railing to use. We decided to use a concrete curb and build railing on top of curb. And at the apartment, we decided to build a concrete diaphragm. So we can use a concrete diaphragm and concrete apartment to build the standard expansion drawings. The last case study is the skull. And skull is the one of the, it can be either number 1 or number 2. Most people say number 1 cause of bridge failures in the United States. And because like the skull was not very well known until like the 1970s. Although people know that very well, but it was not, people did not pay attention to that. And since then, people design bridge to be skull resistant. And so I hope in the future there won't be there won't be many problems because people already designed. Just like for earthquake, for newer bridges, usually you should not have big problem after earthquake. Basically, what is a skull? Skull is like due to the some kind of constraints of flow, water flow, so that water will have like a strange flow, which also produce a concentration type of, similar to stress concentration. It will have like a different directions and different speed or velocity at certain local locations, which is caused by the blockage of the normal water flow. And that, like for example, that pier was damaged because of that situation. So normally, when we consider skull, there's 3 components. One is what we call general skull. General skull is like, even if without the bridge, you may have a skull. In other words, like if you have a river, the water may come. Some area you may actually have accumulation of sediment. In other words, your riverbed will getting higher and higher. Of course, because the total mass is the same. We have higher and higher, which means at certain areas, stream bed getting lower and lower. In other words, during the course of history, the waterbed elevation will change. That's vertically. Also, the stream shape will change too. So that's a natural process. Like has nothing to do with bridge. So that will give you certain like depths. Like you have to assume. Actually, we'll be able to calculate based on the shape of the stream what will actually lose, how much soil you may lose during your 100-year life of the bridge. That's if you have no bridge, or if you have built a bridge from bank to bank without affecting the stream. And once you put the piers in the stream, then that broke the water so that you have narrow channels. Once you have narrow channels, of course, you have high velocity. So that will wash out, produce additional skull. And that skull called contraction skull. That means because you have smaller sections. And then there's another skull, it's called a local skull. Local skull is because at certain location, because the water flow is restricted, so it can have strange velocity directions and velocities, so that will produce an additional local score. These local scores typically will wash out a lot of soils under the footing. So you have to consider all these threes to be able to determine how much the score protection will be required. Like for example, if that bridge would have no piles, then if we build footing there, it will collapse. Or if we have very, very short piles, it may also collapse. And so of course, to calculate scores usually is not a structural engineer's problem. So usually hydraulic engineer will be able to calculate for us. So they will tell us how deep the score has to be and what velocity is. Based on velocity, you'll be able to determine what size of rock or protection you need so that it will not be washed away. So for abutment, typically the score will have like these kind of phenomena. One is like it will score off at the abutment footing, or actually it may score off at the approach to the abutment footing. Sometimes it may just wash out not only in front and back side. So like you may wash out all the approach slabs here too. Like you will see like pictures like these is like represent that, and these represent actually that. For score detections, like sometimes you may use like sonar. Sonar typically is good to score general scoring. In other words, it can detect, like for example, last year the riverbed elevations here, and this year the elevations there, so they will see, well, the score is happening very quickly. That's general. To localize the score, it can detect, but not very accurate. So you still rely on the human inspectors to do a score detection or inspection for local scores. Another actually score inspection is that people may use it to detect frequency. We know that if we have that's typically for very large bridges, when you have like piers and you have many spans and very deep in the ocean. To do a score inspection for each one is difficult. Then you may say, let me see which one I really need to score. So you can do a vibration test. Like for each span, like if we have 5-span bridge, you do a vibration test. And then you will see if the vibration frequency changes. Of course, we assume the superstructure does not change, but if a substructure is become weaker, like for example, if that's very strong, you have, and if we have a score host, each modular will be smaller. So that once you have a weaker support, just like assume you have a spring at support, now the spring become weaker, the vibration frequency will change, so that then you will be able to tell, if you have a span 1 and a span 2 and span 3 has a significant change of vibration frequency, then you probably may know that pier between 2 and 3 may have score damages. Then you can do a detailed inspections. And for, of course, these are the phenomena and detection. For score protections, if you have very straight channels, you may build this kind of shape to protect the scores, protect the abutments. And or you can actually provide some kind of stabilization. Basically, these are just a group of rocks together, and or sometimes you can have piles, group of piles, timber piles together to make the water more resistant. In other words, provide more frictions to the water to slow down the water against your abutment. So that will protect your abutment. That just provide hard shear, like provide a lot of rocks to prevent the water from cutting into that abutment. Or if you have widened the problem, that may be an indication you have problem. In order to prevent that goes further, you can build some like a rock dam or like a dike. Basically, just a small rocks to basically to reduce the water flow. And if you have like this kind of shape, it's the same thing. You can provide like some kind of restrictions to prevent the water going too fast against that. When you do a riprap or when you do the design, make sure that you have to have sufficient cover for the abutment so that water will not be able to wash out behind the abutment, not only in front of the abutment. So that additional riprap is very essential. For the piers, it's the same. You need to provide sufficient riprap to get into deeper than your total score. Total score is like the 3 components we discussed. So once you do that, these rocks will be so the water will not be able to go underneath to wash out materials. Another thing we use a lot is you can use a riprap, but also you can use prefabricated like a concrete block with cable ties. These are flexible, so you just erect these and they can lay down, and that provides very good protection as well. Like for repair construction typically it's better to work under dry condition, especially if you have a very large construction. But for very small local repairs, actually you can repair under wet condition. In other words, underwater repair is okay. But for like if you want to build like if you have the pier, the whole pier has undermining. You want to cast concrete that you may just provide a sheathing, and like a sheathing, usually you just press them up so that you can actually excavate into wet condition, dry condition, and cast concrete under existing footing. And of course, if it's relatively shallow, you can use like dikes. Dikes is just very much like anything. You can use like plastic, like a sandbag, for example, or just like some kind of just dirt with plastic sheet, or sometimes you may just simply use like concrete barriers too. Anything you can block the water will work. That's typical for very shallow, so that you can dewater by pump. If I pump it out. And of course, you can also do underwater excavation and underwater construction if it's relatively shallow and the scope is not very large. So that saves you dewatering cost. Like for example, if you want to do repair underwater, typically what you do is that because you cannot really pump any concrete, you can only pump ground. So what you just make a like foam and put like aggregates into the cavities, and then you just pump cementitious material grouting into these, so that the grouting will form with concrete. And typically this foam can be permanent, they don't have to stay. But if that's relatively shallow, you may not even need any aggregates. You just simply use a grouting material as a repair. You can do the underwater repair, like you can use epoxy to seal the crack. You can use using epoxy materials to repair spoiling, that kind of thing as well. But the quality is not as good. Yeah, underwater repair, again, as we discussed earlier, you can just simply block these user. I typically use concrete bag. Concrete bag can lay down much nicely than the just regular riprap stone, so that once I do that, I just can pump grout into that footings. And again, it's the same, if you have a spray footing and that's a score, and you can provide protections, or you may simply say, okay, let's just build a deep foundations. Once I have deep foundations, even if I have a little bit undermining in the future, if the soil all washed away to here, I will still be stable. And this example, I think that's in Kansas. There's a bridge called Arkansas River. So when the bridge was designed, that's the original design. They have spray footings, but they didn't do score analysis. And finally, actually, now the current that's the original. When the bridge was built, actually they have sufficient depths. I think they have more than a meter of soil, and now the inspector found there's actually no much soil left. There are actually big cavities here already. And then they did a score analysis, and this is a calculated score, which means if you don't do anything, it could happen all the soil will be washed out, the bridge may collapse. So these are the inspection. That's where you see some footing has already exposed, and there's no soil underneath already. So what they did was they cast, first they dewater it and make it dry, and then they cast concrete under they cast 3 times. First they cast one piece of concrete under that footing, and then later they cast concrete in other side, and later they remove soil, cast that. So they cast 3 times. And to prevent the bridge from collapse, you cannot remove all the soils because there's no piles. And actually, they also considered using a deep, at micro piles. Then found the soil underneath is very stiff. It's difficult to drive, so they decided just using regular concrete and without piles. I'll show you the design details. So what they did was, they had they cast 3 times, so they cast all the concrete under the footing. After that, they just they also cast a little bit concrete on the side of footing. Then they cast a reinforced concrete, the whole thing, the top and the side. That side is 9 feet because the score analysis shows there will be 9 feet potential. The score may go that deep. So they built 9 feet cut walls to totally protect that original footing. And that's the plan view. And they also had considered using a much shorter cut-off walls, but with micropiles. And finally, they found it's very difficult to install micropiles. That's why instead they put a very deep cut-off walls and did not have these. Okay, we have all 5 case studies.